Mrs. Sargent, and this is lesson 7.1. What is stoichiometry? So in class we did the s'more stoichiometry to give you a model for stoichiometry, but you've been hearing this word and we haven't yet defined it. So stoichiometry is defined by the process for determining the amounts of reactants and products in a chemical reaction. The Greek meaning for stoichiometry is element measuring. So you're going to want to make sure that you have this definition down. It wouldn't hurt to write down the Greek meaning as well. So we used s'mores as a model for stoichiometry, and then you were able to do some calculations. Those calculations we're going to further look at today and see how they apply to a chemical reaction. A s'more, we had to have a recipe to put it together, and you guys developed a chemical equation to form that s'more. A recipe is like a chemical equation. The ingredients are the reactants. And this says that it yields 4 dozen cookies. So after the yield arrow comes the products. The cookies are the finished product in this chemical reaction. So it yields 4 dozen cookies based off of this recipe. How many dozen cookies can you make if you only had 1 egg? Well, we need to look here, and in this recipe, the recipe calls for 2 eggs. So in your refrigerator, you only have 1 egg. So you're going to start with the number and unit that you're given, and you want to find how many dozen cookies can you make. So 1 egg, and then our recipe calls for 2 eggs, and the recipe produces 4 dozen cookies. So eggs cancel, and we're going to be left with 2 dozen cookies. Now you might say, oh, well, we have half as many eggs as we needed for our recipe, so we're going to take our product and divide it by 2. If you start by using dimensional analysis, this is going to be the tool that's going to help us throughout stoichiometry. So I just wanted to show that to you again and help you become familiar with it. Now, if you wanted 8 dozen cookies, what would you need to do to your recipe? Well, if it yields 4 dozen and we want 8 dozen cookies, that is double the amount. So we would need to double all of our ingredients. So now, those were pretty simple. It was double or half of it. But now we need to make 5 dozen cookies. Say you needed to make those 5 dozen cookies to have enough cookies to bring to school to share with your friends for your birthday. And so you need to adjust your recipe appropriately. So we're going to start with 5 dozen cookies. That's the number and unit that we're given. And we want to know how many cups of flour. It's not an easy multiple of 4, so we kind of need to do some rearranging. So we're going to go with 5 dozen cookies. How many cups of flour? So 5 dozen cookies. And in our recipe that produces 4 dozen cookies, we need 3 cups of flour. So our dozen cookies are going to cancel. 5 times 3 is 20 divided by 4. You should get 3.75 cups of flour. And if you've baked before, you know that it is beneficial to be really precise with your measurements. So you're going to want to have 3 3/4 cups of flour. You're not going to want to just put in 4 cups of flour. And if you had 7 eggs and all the rest of the ingredients weren't a concern, you want to know how many dozen cookies you're making. So think about whatever activity you're involved in. You're having a bake sale, and someone says, how many dozen cookies can you commit to bake for the bake sale? Well, you know that you have 7 eggs. So this recipe calls for 2 eggs. And it produces 4 dozen cookies. So eggs is going to cancel. 7 times 4 is 28 divided by 2. So you're going to be able to bake 14 dozen cookies. So you can tell your coach or sponsor that you will commit to making 14 dozen cookies to sell at the bake sale. So we said a recipe is essentially a chemical reaction, or a chemical reaction is a recipe. You can look at it either way. So in this recipe, we have nitrogen and hydrogen reacting to form ammonia. So in order to interpret this recipe, we're going to say that there is 1 molecule of nitrogen reacting with 3 molecules of hydrogen to produce 2 molecules of NH3, which is ammonia. Now, we call these molecules because they're all covalent compounds. If they were ionic compounds, you would refer to them as formula units. And if it was a single type of element and no subscript, then it would be atoms. So if instead of just having 1 molecule of nitrogen, we double the amount of hydrogen, we're going to need to double everything. So we're going to need 6 molecules of hydrogen, and that's going to produce 4 molecules of ammonia. So these coefficients, they helped us determine the number of molecules, but more commonly, the coefficients represent moles of each reactant and product. So we're looking at the same chemical equation. There's a 1 here, so 1 mole of nitrogen and 3 moles of hydrogen are going to produce 2 moles of ammonia. So if you take a look here, 1, 3, 2, that is the same number of molecules. So the molecules and moles are going to end up being the same number. So that's something to keep in mind. This will help you with your assignment later on. Mole-to-mole ratios are a way to compare the amounts of chemicals in a chemical reaction based off the coefficients. So we said that these coefficients are going to tell us the number of moles. So we have 2 moles of sodium hydroxide and 1 mole of sodium sulfate. So I wrote the mole to mole ratio like this because we are going to use this as a conversion factor to convert from moles of sodium sulfate to moles of sodium hydroxide. I can flip this and convert from sodium hydroxide, moles of sodium hydroxide to moles of sodium sulfate. For water, we have 2 moles of water, and we have 1 mole of sulfuric acid. And then we're still looking at this same equation, and we just said that we have 1 mole of sulfuric acid. So that's not going to change because we're looking at the same chemical equation. And we want to compare it to sodium sulfate. Well, we said there's 1 mole of sodium sulfate. That's still going to be the same. The only thing that has changed is the moles that I'm comparing. Now I'm comparing sulfuric acid to sodium sulfate instead of sulfuric acid to water or sodium sulfate to sodium hydroxide. So we have these 3 questions. The first one says, how many moles of sodium sulfate can be produced from 3 moles of sodium hydroxide? I always like to underline the number and unit that I'm given and circle the unit that I want to find. That kind of just helps me keep my thinking straight. And so we're always going to start with that number and unit that we are given in our problem. So 3 moles of sodium hydroxide. And then we're going to take a look at our chemical equation. Well, we have 2 moles of sodium hydroxide in our chemical equation. And we have 1 mole of sodium sulfate. So now, because these are related in our chemical equation, we can convert from moles of sodium hydroxide to moles of sodium sulfate. So we're going to do 3 times 1 divided by 2, and that's going to give us 1.5 moles of sodium sulfate. Similarly, we want to know how many moles of sodium hydroxide are needed to produce 5 moles of water. So we're going to start with 5 moles of H2O. And in our chemical equation, we have 2 moles of water. And we want to convert to sodium hydroxide. We have 2 moles of sodium hydroxide. We're going to cancel out our moles of water. 5 times 2 is 10 divided by 2. That's going to be 5 moles of sodium hydroxide. And then the last question says, how many moles of sodium hydroxide are needed to fully react with 5 moles of sulfuric acid? Go ahead and pause the video and try this one on your own. Welcome back. So we're going to start with our 5 moles of sulfuric acid. And we want to find the number of moles of sodium hydroxide. So we're in our chemical equation, we have 1 mole of sulfuric acid. And we have 2 moles of sodium hydroxide. So moles of sulfuric acid are going to cancel. 5 times 2 is 10 divided by 1, still 10, and it's going to be 10 moles of sodium hydroxide. So your practice is going to be based off of this. You also need to take out a piece of paper, and we are going to copy down this chart. In class, we balanced this chemical equation in our warm-up. If you need to copy down the chart, go ahead and pause the video. Welcome back. So the potassium chlorate. Potassium chlorate is an ionic compound because potassium is a metal. And so the particles of an ionic compound is going to be formula units. So we have 2 formula units for potassium chlorate. Potassium chloride is also an ionic, so 2 formula units of potassium chloride. Oxygen is a covalent compound, so this is going to be 3 molecules of oxygen. Then we need to determine how many moles of potassium chlorate do we have. Well, we have 2 moles of potassium chlorate. And we have 2 moles of potassium chloride. And 3 moles of oxygen. Now you can see the coefficients go both for the number of particles and for the number of moles. Moles are how we can compare both these ionic formula units and the covalent molecules. The mass. So if we look down here, we're going to take the number of moles times the molar mass. So we need to calculate the molar mass for potassium chlorate. So you're going to look up the average atomic mass for each element and multiply it by the number of atoms in our formula. This should be 3. So we're going to get 48. Um, 35.45. And 39.10. So we need to add these together to get our molar mass. And I believe should be, sorry, I don't have these notes in front of me, 122.45. Or 122.55. And remember, we label our molar mass as grams per mole. But this is just 1 mole. You guys told me that there was 2 moles. So we're going to have to multiply that by 2. And we're going to get a mass of 245.10 grams for the 2 moles of potassium chloride. Now, we don't have any other reactants, so this is going to be the total mass of our reactants as well. For potassium chloride, we're going to look up the average atomic masses and then multiply by the number of atoms. Sorry, my pen's not working here. should get 74.55 grams per mole. And then, this is 1 mole, we have 2 moles. So we need to multiply this by 2. And you should get 149.10 grams. And then for oxygen, the average atomic mass is 16, but we have 2. So that's going to be 32 grams per mole. But we have 3 moles, so we need to multiply that by 3. And this is going to give us a total of 96 grams. So now the total mass of our products, we're going to add 149.10 plus 96 grams, and we have a total mass of 245.10 grams. This is showing the law of conservation of mass that says that matter cannot be created nor destroyed. So because we've balanced out our chemical equation, we found the mass of each compound, the molar mass, then we multiplied by the number of moles that comes from our chemical equation, the total mass of the reactants should always equal the total mass of the products. Okay, so you have practice C in your packet to do, as well as this homework assignment from the book, page 371, numbers 1A and 2A, and page 372, numbers 3A, 3B, and 4B. If you want to write this on the front of your packet under homework number 1, you can do that. That's where it'll be part of your packet grade as well. But you will hand in this book assignment in the next class. If you have any questions, go ahead and come and see me. Thanks for stopping by, and have a great day. Thanks.